Hello everyone, my name is Srinivasa Ippili. I am a PhD student from University of Kentucky, and I am going to be presenting you all my work relating to deep learning based mechanical fault detection and diagnosis of electric motors using directional characteristics of acoustic signals. Let me state what machine learning fundamentally means. Machine learning is an application area of artificial intelligence, or AI in short, where systems automatically learn and improve from experience without the learning being explicitly programmed. While most programs are a set of clear instructions, machine learning is different because here you are not creating explicit instructions. Instead, you give the computer data as well as some standardized learning tools that the computer needs to study the problem and solve it without being told what to do. The computer remembers what it did so it can adapt, evolve, and learn. The machine or computer looks at the input data to recognize some patterns. These patterns are normally found within the data itself. Sometimes you can help the process along. However, strictly speaking, the machine should do the learning and the user does not train the computer. Data is the information we typically acquire from the world from a situation of interest. The machine learns by using old data to get information about what's the most likely to occur in the future. More data normally permits a better prediction. Moreover, the data should correlate well with the desired outcomes or outputs. Once a sufficient amount of data is provided to the machine, then the machine can make better judgments through pattern matching and strategic decision making. In simple words, the machine or the computer looks back the past to predict the future. It is assumed that the history will repeat itself. Hence, machines can predict the future so long as the future doesn't look too different from the past. So, what does it mean to learn? What are the different strategies that we as humans use to learn something new? How can you take these strategies and then apply them to machines? The first way is called supervised learning. In this case, the data scientist or the engineer will train the machine or computer by showing it some basic rules and giving it an overall strategy. This normally involves using labeled information. Another approach is called unsupervised learning. In this case, the machine makes all the observations. It might not know all the different names and labels, but it will identify patterns on its own. This normally involves the machine clustering information into groups. Finally, you might also mix the two and try something called as semi-supervised learning. Here, you train the machine enough to get a high-level overview of what you are trying to accomplish. After that, most of the learning about the rules and strategies is through observing different patterns. As you can imagine, all three approaches have their merits. You can think of machine learning like adjusting knobs and then running a process. The major knobs to adjust are: you first must decide what type of data you are interested in, and that data must be conditioned. Sometimes you might feed in time data, frequency data, loudness data, or so forth. The data may need to be conditioned to remove noise, for example. Secondly, the data needs to be split into training and testing data. Training data is for training the machine learning algorithm, while testing data is for seeing how well they work. Data will also need to be plotted and visualized so you better understand what you are working with. After getting some grasp of the information at hand, select an appropriate machine learning method and algorithm. You might use here either a supervised or semi-supervised or unsupervised approach. Finally, you can adjust a number of learning parameters like the learning rate and the way the data is clustered. What is deep learning? Well, deep learning is a subtype of machine learning that consists of multiple nonlinear processing layers to study hierarchical representations of the data, minimizing the need for human action or usage since its algorithms conduct feature extraction on their own. In recent times, deep learning methods efficiently solved large variety of tasks by utilizing increased computational efficiency obtained from GPUs. This is mainly due to artificial neural networks, which are the building blocks of deep learning. Computer vision has advanced greatly using deep learning. primarily over one algorithm, namely convolution neural networks. Firstly, neural networks are often referred to as artificial neural networks, is a form of supervised machine learning technique that consists of artificial neurons which try to mimic human brain neurons. A single artificial neuron and its similarities to a biological neuron can be seen here. The idea behind a simple artificial neural network is that it is possible to mimic certain parts of the brain neurons using simplified mathematical models involving primarily an input layer, a bunch of hidden layers, and an output layer. Convolution neural networks are designed for image processing with two main sections, feature learning and classification. While our human brains analyze various aspects of an object in an image, such as edges and colors, machines merely see it as a collection of matrices with unique numbers. Firstly, convolution layers systematically apply filters, also called as kernels, to generate feature maps from input images. This is done by calculating the dot product between the kernel value and the image pixel value. The convoluted output shape also depends on parameters called stride and padding. While stride increases the step size of sliding a filter over an image, padding adds empty pixels to overcome the problem of losing perimeter pixels. Next is the pooling layer. The pooling layer reduces large feature matrices to smaller ones, commonly using either max pooling or average pooling techniques. We then repeat this process as needed to enable the network to learn increasingly complex shapes. The goal is to learn to detect complex features that can become trainable classifiers for a list of objects. Finally, we add an artificial neural network to these extracted features. Here, we input the flattened feature outputs to a columnar for final classification. CNNs can use either transformed vibroacoustic data or sometimes raw time series data for fault classification, thereby eliminating the need for human expertise on feature extraction, thus saving time and computational resources at the same time. At University of Kentucky, I performed a research study employing an electric motor fault simulator that's capable of evaluating induction motors with different seeded faults within. The motor's fault simulator is essentially used to generate a dataset for emulating a manufacturing end-of-line fault classification scenario. In addition to a good, healthy motor, three mechanically faulty motors are used in this research study. The three faulty motors correspond to: one, a motor with a centrally bent rotor; two, a motor with a built-in rotor unbalance created by setting up an unequal distribution of weight of a rotor about its rotating central line; and three, a faulty bearing motor with a hole on the outer race. Vibration historically has been the only parameter used for machine health monitoring, but using accelerometers can pose mounting, calibration, and placement issues. Non-contact acoustic transducers, such as particle velocity sensors, can provide a solution to these problems in those applications. They can measure vibration information acoustically and characterize the vibroacoustic behavior even in the presence of background noise, thereby enabling the identification of specific sources despite other acoustic sources nearby. Therefore, the measurement setup I used in my research study included multiple sensors. Firstly, two accelerometers, one placed on the top and other on the side of the motor. Then two acoustic transducers, a microphone, and a PU probe. The microphone is placed about half a meter away from the motor, and the PU probe is placed just on top, about half-inch above the motor. The PU probe here measures two acoustic quantities simultaneously: pressure and acoustic particle velocity in the top direction. The reason accelerometers are also used in these experiments is for performing a final comparison against the acoustic sensors for performance in fault detection. Siemens Cadus hardware and test lab software is used for this purpose of the data acquisition. Measurements were obtained for all the motors at 5 different stationary speeds, ranging from 1000 to 3000 RPM with an increment of 500 RPM each time. Let me present to you all some background on how these electric motors with inbuilt seeded faults compared against one another in various domains. The plot shown here is a comparison of sound pressure level of all the motors when running at 1000 RPM. However, if we compare just the good motor and the motor with built-in rotor unbalance, we can observe that they look very similar to each other. The next plot here is a comparison of acoustic particle velocity measurement of all motors in frequency domain when run at same speed of 1000 RPM. If we just observe the particle velocity data of motor with a bored rotor and the motor with a built-in rotor unbalance, they again appear to be very similar to each other. These plots show that even for a vibroacoustic expert, it can be very challenging to establish discriminative features that can precisely distinguish different motor fault types. The traditional signal processing based features obtained from sound pressure level alone can either become incapable or insufficient, especially when a greater number of operating speed cases and background noises are introduced within the training data. Also, the traditional processing methods demand the need for the end-of-line working professional to have some form of vibroacoustic expertise, which is difficult to always guarantee in a manufacturing setting. Therefore, in situations and for applications like these, we can try implementing deep learning to overcome the mentioned problems. Some of the recent literature demonstrated that the original two-dimensional image-based CNN concept could be harnessed on one-dimensional sequences of data as well. The outstanding benefit of using one-dimensional CNN for motor fault classification is that they can learn from the raw time series vibration and acoustic data directly without the need to perform the data transformation to a frequency domain. A good CNN model will learn an internal representation of the raw time series data and ideally achieve comparable performance to these models fit on a version of the data set with human expert dependent engineered features. Here is the network architecture of the CNN model I have currently defined for this study. It learns to extract starting by from one-dimensional sequences of input observations with 512 sample points each for a selected set of sensors. As I mentioned earlier, these inputs are then transformed to features by using a series of convolution and pooling layers. Batch normalization is a process here to make neural networks faster and more stable. It does so by adding extra layers within a deep neural network in order to perform the standardizing and normalizing operations on the data emerging from a convolution operation in a previous layer. The extracted features are then flattened to form dense layers as input to an artificial neural network that is mapped to one of the four different output motor conditions. Three essential aspects may be identified in the CNN workflow: data loading and preparation, defining, evaluating, and optimizing the CNN model, model testing, and summarizing of the results. As a first step, the data sets required for the training the CNN model are prepared. The vibration measurements are collected at a sampling rate of 12,800 Hz, while the acoustic measurements were collected at 25,600 Hz sampling rate. Each measurement is made for 60 seconds at each speed, then converted and saved to WAV files. The data is imported into a Python model I developed using PyTorch framework that splits each WAV file into small snippets of 512 sample points each. The data sets from each sensor are then individually normalized using min-max scaling. Next step involved optimizing the CNN model using a suitable selection of training hyperparameters. Shown here are some selection of hyperparameters used to train the CNN model. The following plots show the training loss, validation loss, and validation accuracy improved during the training process over 50 iterations. Generally, validation data could be understood as a small partition within the training data, which the machine learning model occasionally sees but never really learns from it. We use the validation dataset results for tuning the model hyperparameters. Therefore, the validation set affects a model, but only indirectly. An L or elbow-shaped curve for loss, as we see here, usually denotes that the training model is converged. Finally, accuracy. It generally signifies the fraction of predictions our model got right. It's important to note here that our CNN model doesn't just predict whether a good good motor or a bad motor. In fact, the accuracy here means whether the model was able to successfully distinguish among different motor conditions as well. In simple words, it's not a binary classification accuracy that is shown here, but in fact, a multi-class classification accuracy. Shown here on the left is a tabular representation of results obtained from CNN model is trained and tested using datasets from 1000, 2000, and 3000 RPM, comprising just the vibration data alone. In each of these tables, percentage split signifies how the whole dataset for each sensor is divided for the purpose of training, validation, and testing. Because accuracy for training dataset and loss for testing dataset doesn't offer any important takeaway, there are hence not reported here in these tables. The next tables show the results from the CNN models, which when trained and tested using datasets comprising different combinations of acoustic sensors. The results demonstrate a very good performance when acoustic data alone, especially the pressure and particle velocity combinations, is used for deep learning based fault classification. Furthermore, it is important to note that the accuracies presented before represent the multi-fault classification accuracy. Um, the two-dimensional TSNE plot here shows us how the output classification features from the learning model spread out beautifully to present us with these excellent clusters, thereby grouping the different motor fault types separately from the healthy ones. I have included a list of some references here. This concludes my presentation today, and I thank the INCE board, the conference organizers, for providing me this opportunity. Thank you.